Hi folks, we're going to see if we can't run this Pasco optics kit experiments or demonstrations using an optics kit here in my basement over here in the corner about next to the wall here. I have a little desk lamp that's providing our light at the moment, probably a lot of glare. I have the printout. My plan is that we'll see what the light does and get an idea of what's going on. And then as we work through this read this video on YouTube, we'll be able to write down the results and then discuss some of the models that we're working with. So I believe I'll probably go through what the kit contains, but obviously this is the picture. Obviously I have this little light housing that has a little vertical light bulb inside of it. It is not a light emitting diode. It is actually a piece of coiled wire. And the coiled wire has electrons running through it, and the electrons running through it bump into each other as they run through this tightly coiled wire. It causes them to accelerate whenever they hit an object inside the wire, and that acceleration causes them to give off photons. So we have this huge stream, this continuous stream of photons coming out of this box. This is just the drawing. We're going to select some of those streams of photons, not photons, sounds like a frozen yogurt, of those photons using this slit plate, which we'll take a look at in a second. And that is going to hit this little tiny disc with some markings on it. It turns out that the disc is not flat. It's actually at an inclined plane to allow the light to hit it as it sort of climbs up the plane. And then there's a viewing screen on the end. Okay, so what I'm going to do is I'm just going to walk my phone over to what it really looks for real, and I think it almost looks exactly like that. Okay, so what do we have here? We have the light box, which is here, and it has a power supply and an on switch. And inside there is a light bulb. I'm about to turn it on, which is a vertical light bulb. The bulb, the reason why we call it a bulb, is it is a vacuum or a near vacuum encased tube of glass with a wire inside of it. And when we light it up with electrons, very similar to the toaster wire inside your toaster, it gets very, very hot and it gets very, very bright. And if we allowed it to hit the air, it would burn, it would catch on fire, and then the bulb would go out. So we have to put it inside this bulb without any air. That's a old school light bulb. We then have this little piece of metal here called the slit plate, which is literally just pieces of slit. I've set it up and I've adjusted it so I don't have to worry about taking time to do that. So I'm trying not to bump anything. And then that slit plate, which is on this magnetic little tiny holder here, this whole thing is on a rail. It's made by the same company that made our cart on a rail with this little tape on the side. Everything is measured in centimeters, obviously. But in front of it is this disc. Okay, and this disc, if I pull to the side here, you'll see the disc is at an incline. Okay, so rather than being flat and having the light sort of miss it, the light is shining on it. So there's some photons that hit here, there's some photons that hit there. So what's happening is this disc is not perfectly normal. It's not vertical, obviously. It's really almost flat, but it's not flat. It's not flat by a lot. I've never really measured this, but that probably is close to 10-degree angle, so that the light coming out of the box shines on its face. And then on the back of that is just something on a holder that holds this little tiny viewing screen. And then, yeah, there's some angles on here. It looks like a compass. There's 0 degrees here, and it goes the whole way over here to 90. And then there's 0 degrees here, goes the whole way to 90. But instead of continuing down to 270, or 180 rather, and then 270 on the other side, it starts over again. So there's 0 on the back, and then 90. And so it's 180 degrees, obviously. But it's 0 to 90, and then 90 back down to 0. I bumped it. I didn't mean to bump it. What I want to do is make sure that is right on top of there, and it is. Okay. Well, this is not how we play with this. We don't play with this with a light bulb behind it. We play with it with the light bulb in front of it. So let's see what we got here. We're going to try to observe the straight line propagation of light. Again, this is our model for our Rey model of light. That beams of light, or parades of light, or columns of light, depending on what model you want to use, travel in a straight line. Okay, and we're going to use ray tracing to locate an object, meaning if you look at the ray over here, you can, if you, oh, my hand's in the way. If you follow the light back, you should be able to find out where it came from. You can trace the ray, you can trace the line of light back to its source. That's what we're going to do. So we did set it up, procedure set it up. Observe the light rays on the ray table. Are the rays straight? Okay, so let's go ahead and do that first. So what I'm going to do is I'm going to turn on the light. Okay, click on. You can see that there's some light here. Here's a shadow. It's hard to see. I don't want to blind my phone, but yeah, whoa, I blinded my phone. There's some light in there. And we can see some light rays on the table, but this gets much more fun when I turn off my lamp. Okay, so I'm going to turn off my lamp. There we go. So it didn't get any brighter. It's just that my phone's camera is reacting properly. The camera in my phone, it's just a 2-year-old standard Galaxy S9 Plus phone. It has an okay camera, but what we have is we have the white light coming from that light bulb, which is a filament of vertical light. It's going through these vertical slits, and the vertical slits are hitting this this ray table here. And again, the ray table is angled up so that you can see the rays the whole way down the side. It's kind of neat. And then if you look at it pretty closely, you can see that it's this center ray here is coming in at an angle of 0, and then it goes all the way here. It's an angle of 0 in the back. So we can see these guys. And this little tiny viewing screen, as it says here, has another millimeter measurement device on it to measure the thickness of things. So it looks like, if I look at this properly, it looks like we have 1, 2, 3, 4, 5, 6, 7. Looks like there's 7 slits. And of course, if I count the number of slits inside the slit plate over here, there's 7. That's why we see 7 of them. But we only see 1, 2, 3, 4, 5 because the other 2 are missing. Here's one on my hand, which is missing over here. And here's one on my hand that's missing over there. So 5 plus 2 is 7. And there's a whole bunch of light on top that's missing the slit plate altogether. So all of this light, there's the light bulb. It's actually an LED light bulb inside my little desk lamp. But all this light in my hand is coming from rays from the light bulb. But because these rays are coming out of the box and going through the slit plate, we can actually look at them one at a time. So yeah, there's our rays. Pretty cool. I'm going to confuse the crap out of my phone by turning this light back on. So I apologize, phone. Go ahead and respond. There you go. So it's computerized and it deals with that. We're going to answer the question. Are they right? How does the width and distinctness of each ray vary with distance from the slit plate? Okay, so let's take a look at that. Come back here and see if we get any closer here. Look at the rays here that are close. And then we'll come out here and look at the rays that are far away. Okay, so we'll talk about this in the video. I'll probably stop it, but I think the rays look thinner here and look thicker there. They may be sharper there, so it's like an eye exam, and they may be more fuzzy over here. So it looks like they're getting wider and fuzzier as they go further away, because they're spreading out is what's happening. There's a concentrated source of light inside this box that's spreading out. If we had this box open and there was no box, it would be a sphere, it would be a ball of light, but we're concentrating it forward. Sorry, phone. Wonderful. Set the viewing screen and its holder aside for the next step. Lower your head. Okay, I'm going to lower my phone until you can look along one of the paths of the rays. Where does the light originate? Okay, so what they want to do is they want us to do what it says here. Let my phone respond. There we go. I'm going to take off the viewing screen back here, place it down, and then they want me to put my eye. I'm going to put the phone down here. I'm going to try to walk into one of those rays. There's one of the rays. Okay, there's one of them. Okay, here's the next one. Okay, there's the next one. And of course, what we're seeing here is every time I walk through one of these rays, there's 7 of them, I'm looking back at the lamp itself. So it turns out that all of these rays, no matter how spread out they are, all of them originate back at the point source or the line source. There's the 7 flashings again. And we can do this with our eyes. I'm doing it with my phone. They originate back at the source. So this is the Rey Model of Light. Again, as I drew on my picture, is a picture of a lovely little sun, a happy sun. Sometimes we put a smiley face on it if we're going to draw a picture. And it has rays of sunshine pulling off of it. These are some of the rays. These rays were created by the slit plate, but there's also rays that we see inside lenses and the like. Let me turn this back on. Sorry, phone. Fantastic. Replace the viewing screen, okay, and rotate the slit plate slowly on the component holder until the slits are horizontal. Okay, so what I want to do is I want to take the viewing screen and snap this back on, okay, and turn this off. We're going to go dark again. Here we go. Let my phone respond to itself. Great. We can see the lights on the back of the screen. There we go. We can view it here. I think I will view it from back here. And what we're going to do is I'm going to take the... Sorry, I'm blinding you. I'm going to take the slits and I'm going to rotate them. I know it's square and it's magnetically attached to this plate. I'm going to spin it. Okay, so we're going to take a look at these guys here. I'm going to sort of move it a bit, see if I can do it with one hand. Okay, I'm going to take it off first because I only have one hand holding my phone. Normally we would be in the lab. There's all the light. Fantastic. Here we go. Here is the slit plate again. And I'm going to... So that's pretty good. I'm going to go ahead and I'm going to rotate it, and we'll see that they're starting to get thicker, fuzzier. All I'm doing is rotating it, and then eventually they start to overlap. In fact, they overlap so much so that they get brighter where they overlap, so that means that they're getting thicker as we go. So there they're not overlapping. There's a space between the individual rays, the columns of light. And now they're completely overlapped. And now, well, I say completely overlapped. They're completely touching. There's no gaps. They're equal. And now they're overlapping. So where they're overlapping, it's brighter. We have more photons hitting. So this is horizontal. The same thing happens above here. You can see where we're horizontal. What we're doing is this bulb, I don't know if you can see it in there. I might turn this back off and turn this back on. We turn this back off and turn on my lamp over here. There we go. And maybe you can see the light bulb inside there. Let me get the light bulb down here. There it is. See how the light bulb, let me even change my, there we go. You can see the light bulb is this vertical filament of wire. It's just a wire hanging there. So it's, so there is our individual little tiny wire. You can see the vertical, it's actually a column. It's like a test tube of light, a test tube of glass with a little wire inside of it. And when we turn it on, now if I turn it on, we're not, again, I apologize, phone, sorry. Close your eyes, phone. You're just going to see light. It's not going to do much. Of course, you saw it, see it, there it goes again, and see it go out. There it goes. It's actually higher. So the bottom part is the holder. The wire is up here. And when I pull this away from there and I go ahead and turn this on, that's the light that we're seeing here. It's just light. If I turn off the backlight, it sees that light. I sure hope I didn't hurt my phone. I don't think I did. And here's this horizontal, and then I can bring these guys back vertical again. So what we're getting is we're getting multiple copies of that thin light because there's an infinite number of copies depending on which rays are flying from which direction. Okay, which is kind of cool. And we're back again. Let's see here, lower your head. How does the width, for what angle of the slit plate are the images most distinct? Obviously, straight up and down. In fact, I inverted it down to 180. I turned it upside down. Vertical, they're most distinct. Horizontal, they're not most distinct. And then we're going to go ahead and go to page 2 over here. On a separate sheet of paper, explain your observations. We'll do that, okay? Our next one is our ray tracing. Okay, let me go ahead and stop this. I'll go get the equipment for ray tracing, and we'll be right back. All right, we're back. I have what we need. What we're going to do is we're going to take a piece of white paper, and we're going to place it on top of this disc after I make this screen go away. I still have the light on, and what I'm going to do is I'm going to take this piece of paper and sort of rest it there. Right there. Cool. I want to rest it against the slit plate so it stays put. There we go. Cool. And then what I'm going to do is I'm going to turn off the light. And now I'm going to see all of these rays on top of there. And what I want to do is I want to take my Sharpie marker here, and I want to trace one of the words that we saw, or one of the things that we're about to see in YouTube is called ray tracing on a computer. It traces the rays that you see and traces them back to where they came from, or it talks about drawing a computerized object and then tracing the rays to the screen, either direction. What we're going to do is I'm going to find out where the center is, which is right there. There's the center. I put a little dot there. And then I'm going to try to draw a nice little line along one of those rays. It sort of wiggled because I'm in the dark. And then I'm going to do this center guy here. Okay, and then this one over here. This is going to be our data, believe it or not, for this procedure. So what I've done is I've simply traced the rays. I didn't do, they're all over the place. This guy happens to be the one that's down the center, because I didn't place this exactly in the center again. There's one over here and one over there, and I know, because I've measured it, this dot happens to be 20 centimeters away from the lamp. That's something we need to measure. We need to measure the distance from that dot to the lamp. We did that. So what we're going to do is we're going to stop the video. We're going to work with this piece of paper and then do some ray tracing, literally, and then see how well the results compare to our model, which of course is what we always do. All right, thank you. Alrighty, we're going to work on the next experiment, experiment 2, the law of reflection. And what we're going to do here is we're going to take the box, of course, with the light we saw before, take the slit plate, we're going to try to adjust it. I think I've already adjusted it. We'll double check that, make sure all of the rays, or at least there's one ray going down the very center of the circle disc, this white disc. And then what we're going to do is we're going to have those rays reflect off of a flat mirror. So I have the flat mirror here. You can see it sort of looks like a Star Trek symbol if you're into Star Trek, or maybe a Klingon symbol. One of the sides happens to be flat. That's a flat mirror. One of the sides happens to be convex, which means it bulges to the outside. That's that guy. And then one of the sides happens to be concave, which is bulges in the inside. We're going to use the flat side, and on the bottom of it happens to be a magnet. Okay, so we get to cover magnets as well. I didn't mention before there's magnets on this rail, so if I touch this, it stays there because there's a magnet attached to it. But what we're going to do is we're going to go over here and turn off the light, and then we're going to check down here, and you'll see that I have one of the rays right along the normal on this disc. It enters around 0 and it exits around 0. Again, it gets less bright on the other side. There's a little control knob up here that allows me to steer this a little bit. If I do this way over there, it changes it, and way over here it changes it. But I want to go ahead and put this back where it was, right in the middle, especially down here. I want to make sure that's nice and straight. There you go, that's centered. And it's centered up there as well. And what I want to do is I want to take this Slit Mask, which is this guy. I think it says Slit Mask. Let me double check. Watch your eyes. There we go. And we're back. The Slit Mask. It's just one. It allows us to pull one of those rays out, one of those columns out, rather than all 7 of them. So what I'm going to do is I'm going to turn off the light here and go back here and take the Slit Mask and hover it over the rays until I pick the center one. There's the center one, and there's the other one. Here's the center one, and I want to put it in the center one. There it is. Put it on it right there, and it is connected. You know what? It's not working properly. What I'm going to do is I'm going to put it on the other side so I can get a better... It too has a magnet. I can't see. It too has 2 magnets, like refrigerator magnets, and I'm going to put it on the other side of the holder, right behind the holder, not in front of it, so I get a nice connection. So I'm going to put this guy here, and I'm going to grab it until a little light show. Boom. Pretty cool. What I want to do is I want to go ahead and do that. There you go. Fabulous. So now I have one slit. So the slit mask. Make sure this guy is that right? Move it over a little bit. That's 2. No, that's 2. I just want 1. There we go. Cool. Anyway, there seems to be a lot of others. I just want that one mask. And then what I'm going to do is I'm going to take the mirror, which I have over here. There you go. And I'm going to place the mirror on this little disc where it says component. So the component is going to go right here at 90 degrees. Okay, so I'm going to put the center in there. going to use my camera here. I want to line it up so that the component is straight along there. And if I look properly, there's a reflection. There it is. There's reflection over there. And there it is over there. I want the reflection to be perfectly right back where it came from, or 0. That means that this guy will be close to being right on the component. Right about there. Cool. Fantastic. So now the goal of this, I won't take data because it's in the dark, but we'll take data when I'm looking at it on the video, is what we're going to do is we're going to spin this 10 degrees this direction. Let's go ahead and call that 10 degrees to the right. So right away, I can see that there is 10 degrees input. This is the input, and this is the reflection off the other side. And you'll notice that it comes back out at, oh, who would have thought? I think I just touched it. Dang it. Put this guy back again, right in the middle. I touched it with my finger because I'm a goof. Don't touch it. Whatever you do, don't touch it. So when you're in the lab working with one of these guys, don't touch it. You want it to be right down the middle. Cool. Again, all I'm working with is I'm working with streams of photons. If this was water, we'd be working with streams of water molecules. Let's try this again. I'm going to spin this 10 degrees to the right. I'm going to call this to the right. Clockwise. How's that? I'm going to spin this to 10 degrees clockwise. There's that guy. And then we can measure where it's at on the other side. And then we're supposed to go to 20 degrees, which is there, and measure the output. And then go to 30 degrees and measure the output. If you're playing along at home, I think you've noticed that angle in equals angle out, or at least darn close to it. It really depends on how precisely I got that right. Actually, didn't do too bad. That's really, that's like 51, but it's close enough. We're keep on going. Here's 60. And, yep. And here's 70. And there's 70. Yep. So again, the light's coming in. The ray is bouncing off this flat mirror and taking off. We're measuring the angle in according to the normal and the angle out according to the normal. And then we finally get to 90. And then something weird happens at 90 because the darn mirror gets in the way. So because the mirror is not continuous, actually see some of it reflecting off this guy over here because there's a little tiny edge there. That is not a flat mirror, that's an edge. So all bets are off. But what we want to do as part of our data is move this back. It sort of feels like a clock. Move this back to 0. And then go the other way. I want to spin it counterclockwise to 10 degrees. And then, of course, there is the reflection. And then go ahead and go to 20 degrees. And there is reflection. 30. I'm pretty sure, with a little bit of error, because it looks like it's not perfectly flat. And I may have touched it, because it sounds like something I would do in the dark. Yeah, that really should be over there at 40. I'm going to hedge my bets. There we go. How about 40 in equals 40 out? How about 50 in equals 50 out? Yeah, I must have touched it. I touched it back. Yeah, they're going to take away my physics license if they were to see me do this during an experiment. I would have used more care to never or to paste down this mirror. I should not have moved the mirror while I'm taking data. But hey, what are you going to do? I'm in my own house in my basement. Leave me alone. And again, now way over here. Wow, it's almost a right angle reflection because of the way this corner is. You can see this corner is almost splitting it in half, and then half of it's going this way, and half of it, well, some of it's going towards the front, not much. Totally depends on how it is. Again, this is just because of the shape of this guy, and we're talking about a beam of light. So we've turned this completely 90 degrees clockwise and 90 degrees counterclockwise and got those measurements. I'll write those down when we're sitting in front of the YouTube, and then we'll take some values and we'll see what the results are. Let me turn some lights back on so I see where we're at. Fantastic. All right, so we're back with experiment 3, image formation in a plane mirror. Okay, there's our picture again, same slit guy, same slit plate, and the same reflecting one on the other side. And then we have our plane mirror here. Now, it says here to use a paper. I'm going to cheat and not use paper. I'm going to go ahead and explain this when we're done. But what we're supposed to do is this. We're supposed to go dark. Okay, there's dark. Oh, you know what? I didn't turn off the lights. in my basement. Hold on a second. I'm gonna put you down. There we go. It's facing the floor. I gotta get off my knees because it's a small little table. Turn off the lights. There we go. It's dark. If I fall and hurt myself, someone call the police. Ugh! Okay, I'm back down again. I'm getting too old for this. We're back. All right, now the lights are off in my basement. And we're back to where we were before. I didn't change anything. We have a ray of light coming in normal over here, right to the center over here. And what I'm going to do is I'm going to remove this slit mask so that now we have a whole bunch of them coming in. If I can do that with one hand. Come on, Bill, you can do it. I want to do it without moving. Oh, I moved everything, so let's go ahead and take this off. There's a magnet attaching the darn thing to it. I've taken the slit mask off, and I dropped the whole thing. There we go. We're back again. Super. And now, what I'm supposed to do is, there's the 0 normal. I want to rotate this so that there is a whole bunch of them rotating here. There we go. Cool. So now we have a whole bunch of rays that are coming out of the slit plate, and they're all traveling in sort of a spread position. And then when they hit this plane mirror, they do it again, but this time now they've moved it over to this side. So it's not a right angle. Maybe I can go ahead and make it a right angle, or darn close to it, something like this. So remember back in Isbt211, when we took a falling mass on the edge of the table and we used a pulley to change the force from straight down to horizontal? Well, a mirror allows us to take the direction of travel, which again, the Rey model says they always travel in a straight line unless they hit something. If they hit something like a reflection, then they change direction and they follow the reflection law. But what we're going to try to see here is when we look this direction, we can see that very bright light. But when I come down here and I use my phone to look in the mirror, I can see those bright lights again. In fact, there's that sparkle pattern again. Okay, it looks like we're in a discotheque. Fantastic. I'm seeing what is over here. Okay, I'm seeing what is over here at a 90-degree angle. It actually looks you can't see it, way back here. That's the virtual, it looks like my finger is in the middle. I can't block the light because the light's not really coming from there. It's just the mirror image of what's going on. And if we were to measure this, we would find out that where we see the light in the mirror happens to be the identical distance to what it is in front of the mirror. So one of the laws of reflection, I almost said refraction, that's next. One of the laws of reflection is, we talked about angle in equals angle out, and plane in equals plane out. We saw that in the previous one. This guy, the distance in front, which is the distance from here to there, is the same as distance behind. It looks like it's way over here where my finger is. If I go ahead and come down here, it looks like my finger is just touching the lamp. And if I got out my camera, if I got out the ruler, I'd be able to find out that that's exactly the same distance. So this law of reflection, angle in equals angle out, plane in equals plane out, and distance in front equals distance behind. So I'm able to see what's going on. That's not a real image. That's a virtual image because there's not really any light back there. I'm seeing light that is coming from the real light over there, but it happened to be bent, or it happens to be reflected off the front of this. And we're going to go ahead and when we turn this light back on, we're going to go ahead and go to the second page of this activity and play with this diagram and see what we can learn with the model. Pretty cool. All right, we're back. Experiment number 4, the law of refraction, not reflection. Reflection was with the mirror, where 100% or nearly 100% of the light was reflected. 100% is difficult to achieve. It's like a 99.9% reflective mirror. This time around, we're going to use a lens. Now, a lens is specifically a device that has rays of light that travel through it. Maybe not all of the light, but a good portion of it. You can see in the picture here that there's a box. Of course, the box is still here. We're back to using the slit plate. We're going to go ahead and use the Slit Mask to just get one of those again. But this time around, we're going to use, rather than using a mirror, we're going to use a cylindrical lens. So here it is in real life. You can tell it's a cylindrical lens because it has the word cylindrical lens written on it. It has a flat edge, just like the flat part of the mirror, and on the back side really is half of a cylinder. A cylinder is a giant circle, a circle, full circle with a height. That's a cylinder. This has been cut in half, or it's been molded in half. This is a piece of acrylic. It's not glass, it's plastic. And over here, what we have is, if I click on this guy here and turn off my light, let my light come back up again. Again, I have all of the rays of light, and I've tried my best. Well, not my best. I tried. Okay, I didn't care. Yes, I did. I tried to get the 0 on the input in the center ray there, and have it be 0 on the outside. Again, I'm setting up the experiment. Yeah, that's pretty good. I can try to get this a little bit better. There's 0 out. Is that 0 in? It's not. So let me go ahead and adjust this guy over here. Adjust that there. Make it a little bit straighter. Make this guy back over here. See if that worked. It didn't. So that's straighter, but I need to move it over. So I'm going to go ahead and move the slit plate to me over here. There we go. That's 0 there. Way off over there. I probably shouldn't bother you with this. This is how we mess these things up. If anybody's interested, no one's interested, Bill. Shut up. My graduate degree is in laser spectroscopy. I spent 4 years living in a laboratory with no light. It sounds like it explains a lot. What I'm going to do is I'm going to stop this and use 2 hands to get that damn ray, now it's in the middle, down that light. I'll be right back. All right, I'm back. I needed 2 hands, sorry. There you go. So 0 in the front and down the normal and 0 in the back. Sorry. Come on, focus. You could. That's not too bad. Wonderful. Again, my war story was that my graduate degree, which took 4 years, was in a room just like this. See how fantastic it is? It's completely black. But it was cool. Lots of lasers. But it needed to be black so our detectors could see things. Pretty neat. Turned out that I was using a detector, much like the detector in my cell phone now. My cell phone's not too bad. It's 2 years old. But the detector, just the camera I was using, was a $25,000 machine, which is pretty cool. But again, it's because technology is expensive when you first use it, and now we get them inside phones. So here's this guy. We're back. All right, so I was able to find just one of those guys in the middle, down the middle. So here's what our goal is. We're going to take this cylindrical lens, and we're going to put it on the component tray here. And my job is to adjust this so that as I do this, right in the middle, it allows the light to come back out exactly straight through. It's not perfect, but it's close. There we go. So I have light coming in from the normal direction, hitting the cylindrical lens. You can see the light going through the acrylic plastic, out the backside, and still at 0. Okay, so that is transmission, but I guess you could call it the refracted ray. You can see there's a whole bunch of stuff going on with other light it's gathering. This is what cylindrical does, but it's bringing it right over there. Okay, so what we want to do is, before, when I rotated this table, we got a little bit of a reflected light. I'm going to do just that. I'm going to spin it. Well, I guess I should spin it clockwise like I did before. I'm going to go to 10. Okay, there's 10. And then now you'll notice all of a sudden a 10 showed up. You'll notice my 10 is not perfectly 10. Damn it, I want this to work out. The reflection shouldn't have a problem. Remember, reflection in equals reflection out. I'd like to get this data pretty awesome. So let me go ahead and get that 10 on the 10. This might be an easier thing to adjust if I have the reflected light. It's just a really minute adjustment. Okay, cool. So 10 in equals 10 out. And over here, I don't have 10. It's more like whatever that is. That's 5, 6, 7, like 7.5 or something like that. That's our first one, so that's 10. 10 there, 7.5 there. Let me go to 20. 20 is on the other side. Go to 20. There's 20. I should get a reflected ray at 20. Hello, phone. There you go. That's close enough to 20. Again, it's supposed to be 20. And then over here, the refracted ray, is it 20? Nope. It's 15 or 14.5. Okay, so what's happening is the refracted ray is not coming out at the correct angle. It's not going straight through. Because this is a perfect circle, you can sort of see that it's changing direction a little bit. It's more pronounced as we move further. Let me go ahead and make this 30 degrees. There's our reflection. 30 is cool. And over here, refraction, now it's at 20 or 19.5. You can sort of see the light bending now. And then over here, 40. I'll be writing this down as we're watching the video. There's 40 in. There's 40 out. There's a lot of reflection going on now. How about refraction? It's over here at 27 or 26 and a half. You can really see it bending now. Okay, remember, light travels in a straight line unless it changes media. Okay, the cylindrical lens, which is acrylic, has a different index of refraction than the air in my basement. Okay, and we'll read about that inside the procedure here. We need to go to 50. There's a reflection over here close to 50. That's reflection. There's the refraction. It's at like 31.5. Let's do the experiment. Go to 60. There's the reflection at 60. Here's the refraction over here at 36.5. It's really bending now. That's crazy. Go to 70. All right, 70 in, 70 out for reflection. Close enough. Oh, it's bent like crazy. This guy is 39.5, almost 40. This is 80. Reflection, 80, close enough. Refraction. Now it's starting to get a lot of distortion because it's not an infinitely large cylindrical lens. What is that, 42, something like that? It's starting to get goofy. And if I go here to 90, which is right in the middle, nothing much happens. It just goes straight through because it's sort of missing it. So that's half of the experiment. Okay, sorry to take up all your time. The other half is to go the other way. We're back to zero again. Let's spin the incident, the incoming, to 10 degrees counterclockwise. There is the reflection. If I stop blocking the damn thing, I can get it there to 10 exactly. How about that? Darn close. And then over here, we get, again with the 7. That's like 7 degrees, the brightest one in the middle. Keep on going. There's 20. 20 input. There's our reflection over there. Here's our refraction. Is over here at 10, 11, 12, 13, 13 and a half, maybe. Here is, going this way, 30. Reflection is 30 over there. And then this guy is 20. Oh, on the other side is 20. So 19 and a half. A lot of in halves. I'm not sure what's going on. 40. There's the 40 reflection. Over here is 25. Sure. 50. Over here is 29. Sure. 60. Reflection. Excellent. That is 35. Fantastic. I'll make sure I'm reading it in the correct direction. I'll go more slower when we look in the video. 70 over here. That is 39 and a half. There's a nice reflection over there. It's supposed to be 70. You can see I bumped the cylindrical lens. Now our data is total crap. We'll have to go back and do it. I'm not publishing it, so we're good. There's 80 over here. Close enough. Past 40, 42, 41 and a half. There's a nice reflection on that side. And then we're going to 90. 90, all bets are off again. Things happen crazy because we're missing the darn thing. bring this guy back. So we're going to take a look at those results and see if they follow our model of refraction, which is this little puppy here. Turn on the lights. Sorry, phone. Index of refraction of 1 times the angle of input 1, the sine of the angle of input, equals index of refraction to the sine of the angle of the refraction. We'll take a look at that, see how well that works. Let's see it. All right, for today's last experiment, they call it an experiment, our last measurement dealing with the Rey model of light, we're going to be doing something called reversibility. And what we're going to do is we're going to reverse the use of this cylindrical lens. Here's the same setup we just had. And when I go ahead and turn out the light, there we go. I didn't do anything. It's just my phone waking up, and I need to turn this way. Fantastic. And we're good. This 0 in, 0 out. Not too bad this time. Okay, we just got done doing the the angle of incidence on the flat side and read the output. We just did that experiment. This experiment requests us to do that again. But what we're going to do is, after we do this the whole way through, we're just going to copy the results we got before without touching it. What we're going to do is we're going to go around to the other side, okay? We're going to run the light backwards through the cylindrical lens. We're going to have the light hit the curved surface first, and then come out the flat surface. And I'm going to make sure this guy is zeroed when I start. So there's 0, and there's 0 in the middle. So I'm going to go ahead and make this 0 up front. Again, this is just me making sure that it's correct. And then over here, I actually need to slide this back and forth and make sure this is 0. I'm not tilting it, I'm just sliding it back and forth, because this is how this guy works. There we go. Line this guy up. Super. Now, what's different about this guy is, again, the light of incidence is hitting the curved surface. What's special about a cylindrical lens is that it always hits it normal, okay? The normal always goes straight through. What's going to be different now is when it pops back out, it's not the acrylic of the lens that's going to cause it to slow down. It's already slowed down as it travels straight through the lens. It's going to be the air that causes it to speed back up, okay? So we should see a reverse effect. We should see a refraction where we get a greater angle on the way back out, because now the light is going to speed back up to its normal speed. So let's go ahead and do this. I'm going to write down, go this direction, and go to 10, okay? So here is our reflected angle, but this time you'll notice it's not reflecting from the round, because again, the cylindrical side is just reflecting right back the way it came. But there is a reflection from the inside of the lens, okay? So there's the lens. It's hitting the back flat surface, and that's causing a reflection there. It reflects and it comes back out. So on the way back out, it is 10 in, and it is 0. It's about 5.5 on the way out. And then on the other side, when it does come back into the air, it is, get some more light here. It is, that's almost 15, 10, 14.5. How's that? So you'll notice the refracted angle is larger than the input angle because it left the air, it slowed down going through the acrylic, but then it sped back up, so now the refraction effect is larger. And just to add things that are crazy, the reflection off the inside is smaller. Okay, remember, the law of reflection is that angle in equals angle out, but now we're doing reflection and refraction simultaneously. Holy crap, I need to deal with all these things. So if you think that doing this math is complex, wait until you have to actually model it inside a computer game and have light go through glass or go through a vase. There's 20 on the input. Here's our reflection. Our reflection is 16, 15.5, a lot of 0.5s. The refraction is way over here at 30, okay? 20 in, 30 out. That's impressive. And the reflection is only here at 15.5. We need more data here. There's lots of light going on here. 30 in, the reflection is 26 out. And over here, the refraction looks to be 45, it's 45, 45, 46, 47, 47 degrees out. Again, it's not the plastic, it's not the acrylic that's bending the light this time. It's the air that's bending the light because it's changing from going straight. You can see that light's going straight in there. It's going straight because it hit this cylindrical surface where the radius is always normal. It's going straight inside, and then the air is causing it to bend. So air can cause light to bend. That's how we get mirages, when the density of the air changes. It looks like there's water on the road when it's not. There's 40 in, 40 in. There, the internal reflection is 35.5. Cool. And over here, the refraction it's getting broader, but it happens to be over here at 66, 67, 68. I'll put that in the middle of 68. You'll also notice, for those of you with a keen eye, that the light is starting to spread out. Not only is it refracting, it looks like it's changing colors. And of course, this is the last activity for the Rey model of light. We're going to need a different model of light to tell us why the hell is our white light turning into colors. When we do this next one over here, and that's, it turns out after we hit 50, this goes away. We get 50. And then over here we get, what do we get here? There's the normal. That's 40. 40, 46, 45 and a half. But you'll notice that there's no light coming out the back side. Okay, in fact, it's really dark. It's not me playing with my phone. It's really, really dark. This is something called total internal reflection. You can see inside there, it's all of the light, or most of it, according to our eye, is reflecting off the inside surface. This is called total internal reflection. If you happen to be a swimmer or a diver, or if you happen to be, it's too late now because it's October, the next time you're in a pool and you go down to the bottom and you look up, you'll notice the sides of the pool look closer than they actually are. What do I mean? It means your ability to look out the top of the water is shrunk because the air actually and the water causes the light from the side of the pool to totally internally reflect, and you can't see outside. It looks like the walls are closing in on you if you look up from deep in the water. If we got the measurements. If I come back here and slowly get a refraction back over here, you'll notice that this other refraction, this is where we're going to start next week when we talk about the wave model of light. It's not perfect, but it's darn close. You'll notice the light, not only does it happen to spread out and it's all over the place, it happens to follow a pattern, and that pattern is red, orange, green, blue, indigo, violet. In fact, you can see the blue and violet on my little tiny finger down here. Sorry, I needed a manicure before I did this experiment. These are the colors of the rainbow, okay? Red, orange, yellow, green, blue, indigo, violet. This is Roy G. Biv. Okay, this is something that Newton, our good friend Newton, who gave us Newton's law for gravity, also played with white light and discovered that white light is this stream of photons that looks white to our eyes, is not only a stream of many, 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 many hundreds, gabillions of individual photons. The individual photons have all kinds of different frequencies and wavelengths. And our eyes happen to see a range of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And that's going to be our discussion when we start talking about the wave model of light, because the wave model of light deals with those different frequencies and deals with those different wavelengths, rather than just saying that's an individual marble, which is kind of cool. Okay, so right here you can see that's sort of where the total internal reflection turned back off again. We had an input of 43 degrees. We had a very bright reflection at 35, 6, 7, 8.5 degrees. And over here, it looks like we had a refraction of nearly 77 degrees, but the light happened to spread out into its Roy G. Biv colors, which is kind of cool. and we're going to be using the model of the wave model of light to describe that as we go. So I'm going to turn on the light. I'm going to freak out my phone because I turned the light back on. We're going to take a look at this for lab, and then next week we'll be moving on to different experiments that take advantage of, or at least show us things that happen because the light is not just a collection of marbles that are spinning at the same velocity, meaning they have the same frequency of spin. It means that this white light contains a whole bunch of photons that is an entire collection of spinning frequencies. They're all called wavelengths or individual frequencies of our light. And we'll be talking about, we talk about the wave nature or the wave model. Okay, I'm out.